Okay, I guess we'll go ahead and get started then, because we're about 2 minutes past. So, hi everyone, thanks for coming to the workshop on spectral graph-theoretic methods for estimation and control. Yeah, my collaborators and I have been excited to present this workshop for a while now, and we hope that this will be both interesting, informative, and potentially useful in your own work. Yeah, so we've assembled, I think, quite an exciting line of speakers from a variety of great locations. Are going to be telling us some very interesting things about applications of this. And again, on behalf of the organizers and myself, thanks for coming out today. Okay, yeah, so a quick overview of the schedule. We're going to start now. We'll have an hour-and-a-half session, an introduction, some talks from Luana Ruiz and Federica Aragoni, a quick coffee break, and then a second session from 3:30 to 5:30 with Kevin Doherty, Yulin Tian, Julio Placed, and Yongbo Chen. Okay, so I think just in the interest of time, we're just going to dive straight into it. So, one question for those of you who maybe have not seen this before is, what even is spectral graph theory, and what is it useful for? Okay, so just to make sure that we're all on the same page, for those of you who maybe have not studied graph theory previously, a graph is just an ordered pair consisting of a set V, whose elements are going to be called vertices, and a set of edges, which are just going to be subsets of vertices, subsets of distinct vertices, or unordered pairs of distinct vertices. So pictographically, we can represent it. It's often drawn in this way, where vertices are just drawn as nodes, and edges are just drawn as straight line segments that connect their endpoints. And if we want to get, so that's a basic, that's a super simple basic graph model. If we want to get a little bit fancier, we can add weights to the edges, which is just an assignment of a real value to each edge in the graph. So the punchline basically is, these are quite simple models. You can basically define them mathematically using a single slide, as we just have, yeah, so they're pretty easy to understand. And so you might ask, okay, well, given how simple these models are, what are they actually good for? Like, what can we actually do with them, right? And the main reason that these things show up in a lot of the work that we do in robotics or machine intelligence applications is that really these provide a kind of natural language for modeling interactions or relations between entities. So, for example, if you want to talk about description, if you want to analyze conditional independence or dependence relations between random variables, you can think of these random variables as being the vertex set in your graph. And if you connect variables together according to their independence relations, you actually get a graphical model that represents something about information or conditional dependence structures in probability distributions. And so those models are called, those specific graphical models are called probabilistic graphical models, and they are used ubiquitously in machine learning and artificial intelligence to describe how to make inferences from data. Similarly, of course, if you think about a graph or nodes in a graph as being locations or waypoints, and you have edges connecting them to represent traversability, you get communications or routing networks or power flow networks, let's say. And if you think, so my collaborators and I do a lot of work on geometric estimation and robotics, and if you think of these nodes as then being objects or poses, and edges as encoding a kind of spatial relationship between these, you essentially get graphs that are called pose graphs that are used to describe, to model geometric estimation or reconstruction problems. And so the basic idea then is, these actually, despite their simplicity, these models actually show up in a lot of different ways and a lot of different applications that we might be interested in working on. And so, yeah, so a lot of scientific and engineering systems then involve the analysis or the study of systems that have some kind of natural graph structure on them. So, for example, communication and routing networks. And the main point here is, given that a lot of these systems have this underlying graphical structure, the main question that we're interested in is, how does that graphical structure affect the properties that we would be interested in understanding for these systems? So in the case of a communications network, some of the things we might be interested in would be, how fast can I move from one node in this graph to another? How fast does information propagate or communication propagate through something like a communications network? Maybe another parameter of interest might be robustness. So for example, if I'm looking at a communications or a routing network, and I imagine, for instance, that some of these links might be lossy or noisy or can maybe fail with some probability, how does the connectivity or the topology of this graph, together with some notion of the certainty of these edges, affect how reliably that network will operate when certain of these links may be prone to failure? So the punchline basically, or really the main way that we use graph theory or spectral graph theory in a lot of our work is that it provides a set of mathematical tools for understanding how the graphical structure that underlies our systems of interest translates into the properties that we are interested in studying from like a scientific or an engineering standpoint, like speed of communication or reliability. Okay, so that's graph theory writ large. What about spectral graph theory in particular? So spectral graph theory is a sub-branch of graph theory that studies relations between properties of a graph and eigenvalues and eigenvectors of matrices that you construct from that graph. So the rough picture for how spectral graph theory works is I'm going to start with some graphical model, like the ones that we saw before. I'm going to somehow construct from that graphical model a matrix or set of matrices, and I'm going to look at spectral quantities of that matrix. So I'm going to calculate its eigendecomposition, and I'm going to look at its eigenvalues and its eigenvectors. And the idea is that somehow those eigenvalues and eigenvectors are going to reveal certain properties of interest from the underlying graph that I care about. Okay, so what's the main, so that's the high level picture. What's the main way in which this actually gets used operationally? The real reason that spectral graph theory is as useful as it is that it enables us to leverage powerful tools from numeric linear algebra to analyze and solve problems in graph theory. And so if you think about a lot of the stuff, a lot of the works that we talked about during the conference today, as it turns out, people that do robotics and computer vision are very, very good at doing numerical linear algebra. All the optimization techniques that we've built for like series and GTSAM and stuff are all built on top of essentially numerical linear algebraic techniques. And so spectral graph theory gives us a theoretical method that allows us to take those core like computational algorithms and retarget them to efficiently solve problems in graph theory. So that's point number one. And the second point is that many of the actual, as we'll see, many of the actual quantities of interest that pertain to the role the graph structure plays actually turn out to be specifically spectral graph theoretic quantities. So that is, they will turn out to be quantities or properties related to eigenvalues and eigenvectors for these matrices that we can build from these graphs. And so this gives us then both a very nice analytical or theoretical framework for studying problems and a great set of computational tools for actually implementing numerical methods to solve these in application. Okay, so that's maybe a lot of sort of high-level, motivation or background, perhaps. And so what I thought I might do is, for those of you who have not seen this before, I thought I might, as motivation for all the talks that are going to follow, start by giving you just a quick tutorial or a quick little worked example that shows what an application of this might look like for a real, actual engineering problem. So, and the one that we're going to use here, I apologize, that slide got a little bit cut off, but the one that we're going to use here is the problem of distributed averaging. And so the problem that we're going to consider is we're going to be given a set of n agents, which we're going to represent as vertices in a graph. So these could be like robots or computers in a distributed system. We're going to have a graph that's going to describe a communications topology between these agents. So in this setup, an edge connecting a graph means that those two agents or those two workers can exchange messages with each other. And we're going to assume, as part of the problem description, that we were given an initial value, Ci, which is assigned to each of these agents. So each agent has some initial value that it's starting with. And what we want, the goal of this problem, is to devise a distributed algorithm that enables each agent to calculate the average value of all of these initial assignments. Okay, so that's the setup. And okay, so why is this an interesting problem? The reason that we're starting with this is that it turns out this problem can be thought of as a simplified or abstracted instance of a lot of problems that show up in machine intelligence. So this is a slight simplification of problems that look like multi-agent robotic mapping, multi-agent synchronization, formation control problems, and things of that sort that are sort of very foundational problems in robotics and machine intelligence. The other thing I would mention about this is you'll notice that this problem actually, the way that this problem is formulated, I want all of these agents to calculate the same value C bar, the same average. So in particular, this is an example of a more general class of problems called synchronization problems. That is, we want all the agents in this network to agree on a common value. Okay, so given that problem setup, then how might we start thinking about solving a problem like this? So maybe the first question we might ask is, we saw before that we need all these agents to reach consensus. We need them all to decide on a common value. And so we might start by thinking, okay, how might we think about quantifying consensus in a network problem like this? And so perhaps one way of doing this would be to say, okay, suppose that I'm just given some vector of assignments. So these are going to be values that I'm thinking of each agent as having. So the ith element of this vector is going to be the value that agent I has. maybe one of the first things I might write down would be like, okay, I've got some graph structure. Agents on either ends of these edges can exchange messages with each other. And so one potential notion of disagreement might be, I'm just going to have agents exchange messages. They're going to compare the values with their own value with their neighbor. They're going to take those differences, square them, and sum them all up according to some weighted scheme, let's say, right? And so what I'll get from this is basically, I can write down a potential function or a function phi that is constructed according to that way. And essentially what this is going to calculate is it's going to calculate sum of squared disagreements between a node and all of its neighbors in this communications graph. And so I can think of this as being a measure of how much disagreement there is in my overall network. Okay, and well, this is a quadratic form. And so like any other sum of squared errors term, it turns out that I can then just take that and purely algebraically represent this using a quadratic form that's parameterized by a matrix, which I'll call LG. And it turns out, just with a little bit of algebra, it's pretty easy to show that each of the rows and columns of this matrix are going to be indexed by an agent number. And I can read off the values of of each of those rows just by looking at the local connections in my graph. So for the row corresponding to agent I, I'm just going to look around at all of its neighbors, and the sparsity pattern of that row is exactly going to be the connectivity of my graph around that agent. So I can translate directly from the graph structure to this matrix. Okay, so a couple simple observations about this. So first off, by construction, I'm adding up a bunch of things that are non-negative terms. And so this function phi is always going to be non-negative because it's a sum of squares. And it's also pretty clear that if I plug in the all ones vector, this thing is going to be 0. And literally that's just because I'm differencing, all my terms that show up in the summation are just going to be 1 minus 1. So the all ones vector is going to give me 0 for this. And so what that tells me then is that the all ones vector is going to be in the kernel of this matrix L that parameterizes this function. And then finally, and maybe a little bit less obviously, it turns out that if G is connected and my vector values X is not in the span of 1, that is, not all the values are the same, then this disagreement, this notion of sum of squared disagreements has to be strictly positive. And the reason for that is, if I have two values in my vector that are not the same and my graph is connected, there's going to be some path of vertices that connects those two, some path of edges that connects those two vertices. And at some point along that path, I'm going to cross an edge where the two endpoints disagree. And that disagreement is going to show up as a positive term inside my sum of squared errors. Okay, so the punchline then is if I just combine these three facts, then I already can say something very interesting about this matrix that I've built from my graph, which is the smallest eigenvalue is going to be 0. The second smallest eigenvalue is going to be strictly positive if my graph is connected. And the kernel of this matrix is going to be exactly the all ones vector. Okay. Okay, so given that background then, one of the first questions that we might want to ask is, okay, so we've said before that we want all the agents in this network to agree on a common value. Can we write down a set of dynamics, let's say, on this graph that will cause that to happen? And so what we just showed on the previous slide is that I've got this function phi. It's always non-negative, and it's 0. It takes the value 0 if and only if that vector values X is in the span of the all ones vector. That is, if and only if all these agents have the same value. So another way of saying this is the agents in my graph are in consensus if and only if the value of this function is 0, which is the same thing as saying the value of this function is minimized. So it suffices to write down a set of dynamics that will let me minimize this function. Okay, so what's the first thing that you would think to do then? Gradient descent, exactly, right. So we're going to do gradient descent, right? Yeah, so we can minimize this function using the continuous time version of this, which is just going to be gradient flow. And because my function is a nice quadratic form, if I just move along a scaled gradient direction, it turns out I can write my gradient dynamics as x dot equals negative Lx. And what we saw before was that this matrix L had this nice local structure that was just dependent on the local neighborhood in the graph around each agent. And so so that's the algebraic description for gradient flow. If I look at the ith row and look at what that specific row looks like, it turns out that this has a really nice interpretation in terms of the underlying graph. So what each agent is going to execute in this gradient flow is, in continuous time, each agent is basically going to look around its local neighborhood. It's going to calculate its instantaneous difference with all of its neighbors. It's going to take those differences and sum them up in some weighted fashion, and that's going to be the adjustment that it makes in continuous time. So super simple algorithm, And the punchline basically is that this gradient flow update is basically just, it's based on just a weighted sum of local differences with it, for each agent with its neighbors. Okay. Okay, so then this actually suggests a relatively simple algorithm for solving this problem then, which is we're gonna start with a connected weighted graph with positive weights. We're gonna have an initial assignment of values to agents at time t equals 0. And we're just gonna run these continuous time dynamics that we saw on the previous slide, where each agent is just locally updating its own values given the disagreement between its current estimate and that of its neighbors. Okay, so the main question then is, given that setup, does it blend, right? Like, does this actually produce the behavior that we want? And so if we look back at sort of what the dynamics that we encoded before and the starting configuration C that we began with, what you might recognize is that this is actually, the trajectories of this system that we've just described are going to be the solutions to a linear time invariant initial value problem. And so if you guys think back to your maybe first course on linear differential systems, it turns out that these actually has a very convenient closed form solution in terms of the matrix exponential. For that graph LG. And because this matrix LG is symmetric, we can say one thing better, which is actually, it turns out that we can write this matrix exponential or calculate this in terms of a symmetric eigendecomposition for the matrix LG. So the way that I would do that is given L, I'm going to calculate its symmetric eigendecomposition. So that's going to give me eigenvalues and eigenvectors, and it turns out that the exponential of that matrix is the same thing as just exponentiating the eigenvalues themselves, and then pre and post multiplying by the resulting eigenbases. And so that's really nice, because if I take this expression for the matrix exponential and I just plug it back into the solution for my system, that is, my solution xt is going to be the exponential of TLG times my initial starting state. What I actually get is, basically the punchline is if I just plug that back in, I can write my solution xt as a linear combination of exponentials that involve the eigenvalues and that are scalar multiplying the eigenvectors. Okay, that is, another way of saying this is, basically I can use the eigendecomposition of this matrix to write my system trajectories as a superposition of orthogonal eigenmodes that are gotten from this matrix LG, which in turn was built from my graph. Okay, promise I'm almost done, very last slide. Okay, so this is, so using this superposition then, I can now just recall a couple of those facts that we derived before. So remember the first eigenvalue we said was always 0. And the second ones and higher ones are always strictly positive. And so what I can do then is I can just think about splitting this term into the first mode and all the higher modes, splitting this superposition. And if I do that, I get an expression that looks like this. And so the key thing to note here is that, okay, what is that first term? That first term literally says, take my L1's vector, multiply it by C. That's going to give me the sum of all the elements in C. And I'm going to divide that by n. Well, that's literally the average of those elements. That's exactly the thing that I'm looking for, is the average of those elements. And so that first term corresponds to exactly the consensus configuration that I'm looking for. And this second term we saw before, all those lambdas are positive, which means that all the terms in that second summation are going to be decaying, and that decay rate is going to be at least exponential with a rate that's controlled by that second eigenvalue. Okay, so the punchline then is what this allows me to conclude is that the dynamics that we defined earlier using this matrix L, in fact, in the limit the time goes to infinity, do converge to the consensus configuration that I want, and the rate at which they converge to that consensus configuration is exactly controlled by one of the eigenvalues of this matrix. Okay, so summary then, we started with a very simple problem, which is I want to get these guys to collaborate to compute some average value. We looked at this graph structure. We used that to write down some notion of a loss. We used that to derive some dynamics that will sort of drive us to consensus. And the main thing that I want to highlight this is that pretty much all the quantity. So we started with a very basic question. We did a couple of pages of linear algebra, enough that we could fit it on a single slide, a couple of slides. But all of the quantities that ended up controlling the behavior of our system were explicitly spectral quantities. They were some combination of eigenvalues, which controlled the rate of convergence, and eigenvectors, which gave us the modes of our system. And so the punchline really is that all the quantities that controlled the behavior of our systems were spectral quantities. And this is not a coincidence. This is very much in line with the kinds of things that you would expect to see when analyzing the behavior of algorithms that are defined over graphical data structures. So I wanted to do this a little bit, to start with this, just to give some flavor of what do these things look like and why are they useful. So this was a specific case, of course, so I thought what we might do then is just to sort of set the scene for some of the following talks, we might talk a little bit about, okay, what are some, now that I've hopefully convinced you that this is a useful set of techniques to consider, for those of you who haven't seen it before, I thought what we might do is maybe just say a little bit about, okay, what are the common objects that one would commonly expect to see, and what are they useful for, what do they really represent, as a quick tutorial. So for that, I'm going to turn it over to my colleague Kasra, who will do the second half of that.
So welcome. So thanks for coming, and thanks for still being here after David's part. It looked a bit dense. But so I'm going to introduce some basics. So the goal is that these things hopefully are going to help you follow the invited talks much easier. And also I'm going to show you one or two cool things about spectral graph theory, but this is not exhaustive by any means. We couldn't fit many of the mind-blowing results, but I'm sure you're going to see more of that in the following talks. So before I start, let's assume that my graph has n vertices. It's useful to think of vectors of size n, so real vectors of size n, like x, as a function that assigns value to each vertex of the graph. So if you look at the vector x, if I look at the second element of that, x2, you should see that in these talks as a function that assigns value x2 to node 2. So here I'm picking some arbitrary ordering of the nodes of the graph, and I'm labeling the nodes by 1, 2 through n, right? So I'm going to borrow some terminology from from graph signal processing. So there you can call these graph signals. This is going to make me save some time. And it's obvious that if I multiply a square n by n matrix, if I multiply a graph signal, a vector of size n, by a square n by n matrix, I'll get another vector of size n. So I'm essentially getting another graph signals. So I had values for each vertex of my graph. After this operation, I'll get another set of values for vertices of my graph. And you can imagine, you can put any n vector there. It's useful to think about the constant vector. So that's the vector of all ones that we saw in David's part. You can put binary values if you're thinking about clustering and partitioning your graphs. You can take a matrix and compute one of these eigenvectors, and the eigenvector gives you values for each vertex of the graph. So let's say you pick one of the eigenvectors, you look at the fourth element of that, that's the value associated to node number 4 in your graph, right? So this perspective is going to help us to better follow the rest of this talk and maybe some of the following talks. So the first matrix that I'm going to introduce is the degree matrix. So degree of a vertex in a graph is simply the number of edges that are coming to that vertex. So if you look at vertex 4, there are 2 edges coming to that vertex, the orange edges. So we say that the degree of that node is 2. Now, if you just put the degrees on the diagonal of a diagonal matrix D, that just gives you the degree matrix, right? So for example, if you look at the matrix at bottom right, the 4, 4 element is 2, which is the degree of node number 2, right? And in many applications, I think as David mentioned, it's very natural to think of edge-weighted graphs. So you should see edge weights as positive numbers associated to edges of the graph. And then you can generalize this notion of degree very naturally to the case where the graph is weighted by just, instead of counting the number of edges that are connected to a vertex, just add up the weights of those edges, right? So that's going to be a very similar diagonal matrix. So degree matrix itself is not that interesting, but it can be used as a building block to build more interesting matrices of graph and also normalize them, etc. The most natural way to represent a graph with a matrix is probably the adjacency matrix that I'm sure many of you have seen. So it's a symmetric n by n matrix, and it essentially reflects the adjacency structure of the graph. So nodes, so rows and columns correspond to the nodes, and you get a non-zero element at element ij of the matrix if there is an edge between node I and node j. So something that can help you later to detect these matrices in some of the works that you're doing is to recognize the action of these matrices on graph signals, on vectors of size n. For example, if I had a graph signal x, if I act on it by matrix A, and if I look at the ith element of the resulting graph signal, this is just going to be the weighted sum of neighbors of node I, right? So ni is my notation for the neighborhood of node I. The next matrix is the oriented incidence matrix of graph. So in this case, I'm assuming the graph is directed. So you can see the orientation of edges shown with arrows on the graph on the right. So this time, this is going to be a rectangular matrix. You should think of it as rows corresponding to the vertices of the graph. And for each edge, you get a column in a matrix. So what you put in that column for each edge is sort of an indicator vector for that edge. So it's going to contain many zeros. If you, for example, look at the rightmost column of the matrix, it will only have 1 + 1 and 1 - 1. And these correspond to rows that are associated with the 2 endpoints of that edge, right? For example, the last column corresponds to that green edge in the graph. So that's why you get 1 and the first and the third row being non-zero. Again, you know how it goes. So to be able to recognize the action of B transpose on graph signals, this doesn't give you a graph signal. It gives you a vector of size number of edges. And the kth element of that vector is just going to be the difference between the value of the graph signal at the two ends of that edge, right? So for the orange edge, I'm going to get something like x3 minus x1. Now, the main character in graph spectral theory and spectral graph theory is the Laplacian matrix. And you can define Laplacian in multiple ways, but just since we already know about the degree matrix and adjacency matrix and incidence matrix, it's good to know that you can write L as the degree matrix minus adjacency, or you can write it as incidence matrix, some weight matrix W, and incidence matrix transpose. So the weight matrix is just going to be a huge diagonal matrix of size number of edges by number of edges, and you put the weight of edges on the main diagonal. Again, you know the drill. So the action of L on a vector X on a graph signal X, if you look at the ith element of that, you get something that we already saw in David's talk. So you get weighted sum of differences between the value of signal at node I and its neighbors. So you can look at this quadratic form that we saw. So it's not surprising that this L is the same L that David talked about it, but he didn't explicitly call it Laplacian. So if you form the quadratic form associated to L, you get that weighted sum of squared differences across edges of the graph. So we have already seen that, but it turns out that it's more natural in many applications to associate to L, to recognize L, to recognize it through the quadratic form. rather than a linear operator acting on graph signals. Okay, so since we now know that this L is the same L, I'm just going to go quickly through some of the properties of the eigenvalues and eigenvectors of L, but this is not new. So I'm going to, the matrix is symmetric, so I'm going to have real eigenvalues. We always know that the first eigenvalue is going to be 0. And we know that the matrix is positive semi-definite because the quadratic form was literally sum of squared errors, right? Now, as we know, if I put the constant vector, constant graph signal, all the terms in that quadratic form are going to be 0, and you can conclude immediately from that that there's an eigenvector of all ones. And something less obvious is that number of connected components of the graph is given by the number of zeros in the spectrum of L, right? So a connected component, I have an example on the right. So if you think of this whole thing as your graph, we have 2 connected components, right? So these are 2 subgraphs that themselves are maximally connected, but they cannot, they're not connected to each other. There's no path from vertices in one to vertices in the other one. So that's good. Now, what can we do with, if we look at graph eigenvectors and eigenvalues? I've just listed a bunch of things, and the list is obviously much longer than this. And I'm going to cover 1 or 2 of these depending on how well we're doing with time. So the first thing that I'm going to talk about more is it allows you to measure the degree of connectivity of your graph. And as you can imagine, that's very important, right? For example, in David's example, the rate of convergence to the consensus state was determined by some eigenvalue of Laplacian. And as we will see later, that there is a relation between that and how well connected the graph is. So this is very important in any application that involves a graph or a network. You can study diffusions and random diffusion processes and random walks on graphs. I'll talk more about that. You can quantify notions, intuitive notions such as centrality. So what is the most influential node in your graph? And again, you can imagine this is useful in various contexts. Some of the original works that was done in this area are about partitioning your graphs, finding structures in your graph, doing clustering nodes of the graph, finding communities. So these are well-connected parts of the graph that are loosely connected to the rest of the graph. You can think about how, in a principled way, you can approximate graph. For example, how can you approximate a graph with a sparser version of it? And what's the figure of merit there? You can start looking at drawing graphs. So if I give you a graph, it's a purely combinatorial object. It's just a bunch of connections between pairs of vertices. But you might want to map each vertex in a graph into, let's say, Cartesian coordinate of that vertex in some Euclidean space, RK, right? These tools allow you to do that and reveal structures in your graph in the way the graph nodes will be embedded in that space, and many more. I'll start with the connectivity. So we know what it means for a graph to be connected or disconnected, but that's just too coarse, right? There are many graphs that are connected, but obviously some of them are better than the other one in terms of the degree of connectivity. So definitely we need a way to better measure that in a finer way. And if you think of how you would do that, you need a function that takes a graph and it gives you a score, connectivity score. And it makes sense to think of that score to be non-negative, right? So I get a graph, I give you a score, and that's going to be greater than or equal than 0. Now, for this to make sense, again, by definition, we're assuming that that function is non-negative. It makes sense to assume that if I give you a disconnected graph, I should get 0 and vice versa. And you want it to be monotone with respect to the edges of the graph or weights of the edges, right? So if I give you a graph, you measure its score, connectivity score. If I add an edge or increase the weights of the edges of the graph, you would be surprised if the score goes down, right? So these are the basic things that we expect. And it turns out that there are many spectral ways of measuring connectivity that satisfies those axioms. The first one is called algebraic connectivity. So that's the same lambda 2 that we saw in David's talk. Back then, we didn't know that's Laplacian. This is again called a Fiedler value as well. And there's no unique way of measuring connectivity. So each of these kappa functions that you might have, they measure a certain aspect of connectivity, right? So if you define what you care about in terms of better connectivity differently, you would get another measure of connectivity that also satisfies those axioms. And the other one is something that I've worked on it myself a lot. That's what I call tree connectivity. And that's related to how many spanning trees you have in a graph. So spanning tree is a subgraph of your graph that goes through all the vertices of your graph, but it's a tree. And a tree means that it is connected, but it just doesn't have any other additional edges, which can create cycles in the graph. So if you look at the original graph here, and if you look at the orange subgraph, that's going to be a spanning tree because again, it goes through all the vertices, and it's connected, but it doesn't have a cycle. This would be another spanning tree for the graph. And it turns out that you can count these number of spanning trees, again, by looking only at the spectrum of Laplacian. So if I multiply all the non-zero eigenvalues of Laplacian and divide the result by n, that gives me the number of spanning trees, or if the graph is weighted, a weighted generalization of them. So the algebraic connectivity, it turns out that it measures how, like if algebraic connectivity, let's say, is small, it means that you're able to partition the graph such that you can take out a huge part of the graph in terms of number of nodes, but only cut a few vertices, a few edges between the two parts where you're partitioning the graph, right? So it is related to notions of communities in graph. You can look at lambda 2 of different matrices. You can look at the lambda 2 of the Laplacian or lambda 2 of normalized Laplacian that I haven't defined yet. But so this is the way lambda 2 measures connectivity is looking at these these well-connected parts of the graph that are sparsely connected to the rest of the graph, right? This might be a good thing or a bad thing depending on application. If you're modeling an estimation problem, you want all the variables to be connected together well. Similarly, in a communication network. But if you are looking for dividing a problem into pieces and then solve them jointly, or if you're looking for communities, you would want the graph to have such structures so you can break it without destroying too many edges. So I'll skip the second applications because we are 10 minutes behind, but maybe I can quickly go through that. So if you take the adjacency matrix, you normalize it by dividing each row of the matrix by the degree of the corresponding vertex. It gives you the normalized adjacency. And if you've seen Markov chains and random walks on graphs, this is essentially going to be the transition matrix of a simple random walk for the graph. And it turns out that under some regularity conditions, if you keep track of the probability of where you are on the graph, and in each round, just look at the neighboring vertices and pick one uniformly at random. And if you continue doing that, your probability of where you are converges to some probability distribution called the stationary distribution of the Markov chain, and it remains constant after that. And this turns out to correspond to the dominant eigenvector of n transpose. And you can use this to define a notion of centrality, a notion of how influential the vertices of your the vertices of the graphs are, right? So if you continue this chain for a long time, you're going to be with different probabilities at different vertices, and you can see that as how well connected that vertex is to the rest of the graph. And a fancier version of this is essentially what Google did for the Google's PageRank algorithm, where vertices correspond to the web pages and edges correspond to links. And we are doing the random walk for them, essentially. So if you compute the scores, for example, for this example, it's going to be this, but this is a little bit boring because the graph is unweighted and undirected, but you get non-obvious results if you apply to more complex situations. So it turns out that this has many applications. We're going to see many of that in the following talks. I'm going to skip that. Now, how you can use this in your work. So first of all, it's a powerful tool to have your toolbox, right? But we thought about this, and I think there are two specific ways that you can benefit from these. One is that you might be naturally having a graph, at your hand, and you want to study the graph, you want to perform those operations on a graph, partition it, et cetera, then it's immediately clear that these tools are relevant. But a slightly different scenario would be that you might be working in an optimization problem, probabilistic modeling problem, control problem, et cetera, that naturally has a graphical structure. And maybe you were not paying attention, but now that we know about these matrices and their actions and these quadratic forms, et cetera, you might be able to recognize these usual suspects, these matrices that we talked about that often pop up in those applications, and then express your problem in terms of those matrices, and then benefit from knowing about spectral graph-theoretic results by using the results that are already established about those matrices. And I'm going to finish here. So the way we think about, so first of all, if you remember, I picked an ordering of the vertices of the graph. But as you know, the graph doesn't come with an ordering, right? It doesn't come with vertex labels. It turns out that all of these eigenvectors and eigenvalues that we're looking at, they play nicely with permuting the order, the labels of the graph, right? So my eigenvalues are going to remain fixed if I permute rows and columns of the matrix in a symmetric way. Similarly, the eigenvectors are going to be permuted in a correct way so that you still get the correct value corresponding to the correct vertex. So that suggests that these spectral graph-theoretic objects are really looking at the intrinsic and canonical truth behind the graph, not the particular ordering where we are choosing to be able to build those matrices. So that's a good sign. And the last thing is that the same way in signal processing, we grab a signal and we perform Fourier analysis on it to see what's really going on there. And the same way in linear algebra, we take a symmetric matrix and do eigendecomposition, and that tells us about what's really going on about the corresponding linear operator. Spectral graph theory gives you the same thing. So you take a graph, you put it through the spectral decomposition, and then you'll know what's really going on inside your graph. So we're done with the boring stuff. So coming up next, we have Luana Ruiz. She's currently a postdoc at MIT, but she'll start as an assistant professor, I think next month in Johns Hopkins University. We don't have time for questions, but please come chat with us during the break.